By measuring the temperature change of the surroundings during a chemical reaction, it is possible to work out the amount of energy entering or leaving the chemical system. The simplest way to do this is to carry out the chemical reaction in a coffee cup calorimeter. If the contents of the coffee cup heat up, this means the system, that is the reactants and the products, have lost energy, and this energy has been used to heat the solution. The reaction is then exothermic, and the value for delta H will be negative. If the contents cool, then this means energy has been taken in from the surroundings and transferred to the system, and the reaction is endothermic, with delta H being positive. Let's work through an example where zinc powder will be reacted with an excess of copper sulfate solution according to this reaction. We will first monitor the temperature of the copper sulfate solution for 5 minutes before we start the reaction to get our initial temperature. We will now add 0.5 grams of zinc powder to 100 centimeter cubed of copper sulfate solution and monitor the temperature as the reaction proceeds over 30 minutes. By extrapolating the cooling curve of the temperature back to the time when we added the zinc, we can find the maximum temperature difference. Here the initial temperature was 23 degrees C, and the maximum temperature by extrapolating the cooling curve back was 31 degrees C, and so the temperature difference, delta T, was 8 degrees C. We can now use this in our equation to determine the quantity of heat transferred, which is Q is equal to mc delta T, where Q is the amount of heat transferred in joule, m is the mass of the material being heated or cooled, which in this case is the contents of the coffee cup, and C is the specific heat capacity of the solution, which we are given as 4.18 joules per gram per Kelvin. We will then take the density of the solution to be 1 gram per centimetre cubed, and so 100 centimetre cubed will translate to 100 grams for the mass in the equation. When doing this, it is important to note that the mass is the mass of the material being heated up or cooled down, and it's having its temperature measured. We can then insert our values into this equation. The quantity of heat exchanged with the surroundings is 3344 joules. This quantity of heat is for 0.5 grams of zinc. We need to find the quantity of heat for 1 mole of zinc, since there is 1 mole of zinc in the balanced chemical equation. To find the number of moles of zinc, we use the triangle here to get the formula N is equal to little m, the mass of the substance, divided by big M, the molar mass. The molar mass of zinc is 65.4 grams per mole, and so the number of moles of zinc reacted is 7.645 times 10 to the minus 3 moles. If we divide the value for Q above by the number of moles of zinc, this will give us the quantity of heat exchanged for 1 mole of zinc, and is 437,541 joules per mole. To convert this to kilojoules per mole, we divide by 1000. Since the temperature increased, this means the system, the reactants and products, have lost energy, and so the value for delta H is negative, and the enthalpy change for the reaction is minus 438 kilojoules per mole. We can find the enthalpy change for combustion of a substance by burning the substance and using the heat evolved to heat a known mass of water, and then determining the temperature change to find out the quantity of heat exchanged. This can be done in a laboratory using a spirit burner. Let's work through an example of the procedure for doing this with a spirit burner using ethanol as the fuel. First, we add the substance we are studying to the spirit burner and record the mass. We take 250 centimeter cubed of water in a copper beaker, clamp it, and monitor its temperature for 5 minutes to obtain the initial temperature. We then light the burner and use it to heat the contents of the copper vessel until we get a significant temperature rise. We then extinguish the burner and reweigh to find the mass of ethanol burnt. We continue to take temperature measurements so that we can get the true temperature change accounting for the thermal lag. We extrapolate the linear cooling portion of the curve back to the time at which we lit the burner to get our maximum temperature reached. By subtracting this maximum temperature from the initial temperature, we get the temperature difference delta T. We can then use our equation. Q is equal to mc delta T, and we will use the value of C for water of 4.18 joules per gram per Kelvin. The value for Q is then 250 times 4.18 times 41. This will give 42845 joule. This is the amount of heat exchanged between the system and the water for 1.9 grams of ethanol. With enthalpy changes of combustion, we need to find the energy exchanged for 1 mole of substance being burnt. We find the number of moles of ethanol burnt, which equals 1.9 divided by the molar mass of ethanol, which is 46 grams per mole. Then, if we divide the quantity of heat exchanged by the number of moles of ethanol burnt, we find the quantity of heat exchanged for 1 mole of ethanol. To convert this to kilojoules per mole, we divide this number by 1000. The temperature of the surroundings, in this case the water, increased, and so the system lost energy, and consequently the value for the enthalpy change of combustion is minus 1037 kilojoules per mole. The errors in this kind of measurement are mostly related to the assumption that all the heat produced is transferred to the water. Obviously, some heat is transferred to the copper beaker, and some to the surrounding air. We can reduce heat losses due to the air caused by drafts by placing shields around the burner. We can also place a lid on the copper vessel. We are also assuming that there is complete combustion of ethanol to carbon dioxide and water, and in practice some incomplete combustion will occur, producing carbon solid and carbon monoxide.